Okay, perfect. So as Nisha said, welcome to this Powering Up Your Research with GPUs on NeSI webinar that will co-present with Chris. Oops. Just a little bit of an outline of what's the menu for today. We'll have a brief tour of the hardware available on NeSI, a bit of a technical introduction of this. If you're not too much into the numbers, please stick with us because then we'll have a bit more of a presentation into how do you use the GPUs on NeSI, the different way to access them, and what are the sort of the patterns to use them and the technologies to be aware of. And then we'll switch on a handful of case studies, which we hope you'll find exciting and to see what sort of research people have been doing on NeSI using our GPUs. And finally, we switch to a Q&A and feedback session, which is meant to be a bit more informal, and we'll actively ask you questions to know more about what you'd like to see on the platform or how you've been using the platform so far, and things that work and maybe things that work a bit less. And on that note, because we want to have a few things to discuss at the end, we really encourage you to have a look now to the QA document, which is again at the URL that Nisha pasted in the chat. And so you'll have a first section with the general questions and comments during the presentation, if you have anything you want to ask about. But in addition, we'll ask you to think about these questions, which is, have you used the GPUs on NeSI before? And how did it go? Did it go well? Oh, not so well. If you did not use them, what stopped you from using the GPUs? And in general, outside of the NeSI context, what do you use to run your code on GPUs? And we're curious about sort of software and toolchains you're using, and also what you would like to see next in the GPU space on NeSI in terms of hardware, software, training. So think about this, and if you have some ideas during the webinar, don't hesitate to put your ideas in the QA document. This being said, now let's introduce our GPUs. So apologies, the timescale is the timeline is not at scale, but I think you get the idea. In the past, we had in 2018 the first GPUs on the platform, the P100 GPUs, and then a few years later, we had the chance to acquire a bunch of PCIe A100 in 2021, and the most recent additions are the HGX A100. Which have been put in production in between 2022 and this year, 2023. And now we'll review a bit the characteristic of each of these three GPUs and see how they differ and what are their different strains. Okay, so let's start with the grandparents, the P100. So as the name suggests with the P, it's a Pascal architecture, which has been put on the market by NVIDIA in 2016. These are PCIe cards, and they have 12 GB of memory, which is quite nice. And in terms of peak performance, they have roughly 10 teraflops in single precision and 5 teraflops in double precision. And I'll just like to highlight the second point, which is not common for this type of GPUs to have such a good double precision performances. So even if they're not so recent anymore, they have a decent double precision performances. At the moment, we have 14 cards on the NeSI platforms. We have 9 cards on Mavica and 5 cards on the Maui ancillary nodes. And most of them are, so we have a mixture of 1 GPU per node or 2 GPU per nodes. Okay, so now a bit more exciting, maybe the A100s. So this one are Ampere architecture, which has been put on the market in 2020 by NVIDIA. They're again PCIe cards, but now they have 40 GB of memory, which is a huge improvement. And if you have very large data sets that you want to, models and data set actually that you want to put in the memory of your GPU, that's quite nice. In terms of raw performances, it's roughly doubled what we had with the P100, so about 20 teraflops in single precision and 10 teraflops in double precision. However, there is this nice thing that I've highlighted here in red, which are these 156 teraflops of TF32. What's TF32? We'll get back to this in a moment, but in a nutshell, it's what's called TensorFloat 32. And also 20 teraflops double precision if you use the tensor cores, abbreviated here with TC. And this is part of the new technologies in this Ampere architecture, and also in the previous ones, the Volta and the Turing architectures, and that makes a huge difference in terms of performances if your code can leverage this part of the hardware. After some internal and user testing, we witness from 2 to 6 times speed up on the same code when compared to the P100. So it's quite a nice improvement without changing anything else. At the moment, we have 7 cards on Mavica. So it's a mixture of 2 GPUs per node and 1 GPU per node. Okay, so let's get a bit more into the details of why this Ampere architecture. I mean, what are the specificities that make it very exciting? So first, I'll talk a bit more about the tensor cores, these kind of specialized units that give us these large performance improvements. So an tensor core unit is a dedicated, a specialized unit for matrix-matrix multiplications, and in more details actually, is doing a specific operation called a fuse, multiply, and add operation, and that's what you can see below, where we multiply the matrix A and B, and we add a matrix C at the end. And here's the trick. In addition of doing this operation, it supports what's called mixed precision, which means that you can have a lower precision here depicted as FP16, so single precision for A and B, and you can add this to another matrix, which can have a higher precision, like floating point 32, so single precision. And then the results of this can be put back into a matrix which keep the higher precision. And the advantage of this is through some careful design, you can avoid losing precision during this operation. And the tensor core units have been really specialized at doing this operation in parallel. How does that combine with this TensorFlow 32 that I just mentioned before? So the TensorFlow 32, you could think about it as a new numerical representation. However, it's only used internally, so within the tensor cores, and it's a different way to represent your single precision data, so FP32, but with a reduced precision. So the mantissa, the amount of bits for the mantissa, goes from 23 bits to 10 bits. So you lose a bit of precision here, but not a range because you keep the same exponent, but you still have a larger range than what you would have with a single precision. So it's a bit of a trade-off between this FP32 and FP16. And by reducing a bit this precision, we can have an acceleration in the tensor cores. So if your code can leverage this kind of precision, long story short, you can use the tensor cores and have bigger throughput. An additional thing that we had with the A100 is the ability to slice and dice them in smaller components, and that's called the multi-instance GPU mode, or MIG. What's very nice for us to have the MIG mode, it means that we don't need to give a full A100 to the users. We can partition them in multiple smaller GPUs, so we have more GPUs, less performant. And the way users use these smaller components is very isolated. So one user will not impact another user on the same hardware, so they have their own slice of the hardware. And the way we decided so far to use them is to use the finest grained partition in 7 slices. That's why we call the A100-1G.5 GB. And each of them has 5 GB of memory, so it's quite small. But the way we deploy them is to dedicate them for development and debugging. And that's why we restrict people to have 1 Slurm job per user, either via, if you access them using the usual SBatch srun, or if you use them through the interactive Jupyter interface. But that way you can have a very small GPU, but you can test, for example, okay, is the driver recognized correctly, or does my code compile and can run on a small test case? So these are sort of the scope of using these GPUs. Okay, and now our last piece of hardware, the nice HGX A100. And here I'll talk about HGX boards and not cards, because each board actually contained 4 cards, as what you can see on the right hand side. And we have 4 of these at NeSI, so we have 4 nodes, each with 4 um, A100 cards on each. And there are 2 new things on these cards, which makes them very exciting. The first one is a doubling of the memory, which is very nice to have 80 gig of memory per card if you want to train even bigger models. And the other thing which is very interesting is this NVLink interconnection, and that's a direct GPU to GPU connection. It means that if you need to do data transfer from one GPU to another one, you don't need to go through the CPU, and that's very important when you want to do, for example, multi-GPU training. You do want this acceleration. On top of this, we deployed these GPUs on the HGX partition, which is part of the Mavica extension. And what that means for the users, it means that alongside the GPUs, they have access to AMD third generation EPYC Milan CPUs, and they have 256 cores, logical cores, which is quite nice to have. Just to give you an idea of what does that mean to have NVLink versus not having NVLink, we did a little benchmark using the Detectron 2 toolbox. So the Detectron 2 toolbox is a Facebook AI research object detection or semantic segmentation toolbox. And what's very nice with this toolbox is it provides a lot of pre-trained model, and a lot of standard data sets are easily accessible and everything. So here, the task we focused on was to retrain a ResNet 50 model using the standard COCO 2017 data sets. And we tried in between 2 and 8 A100s, and with PCIe or with HGX nodes, and sitting on the same node or different nodes. Long story short, what you can see on the right, I don't know if people can see my pointer. Do they? Yep. Oh, perfect. Thank you. So if we start from the left, we have these 2 PCIe A100 on 1 node or 2 nodes. It doesn't really make a difference. And they take about, well, slightly smaller here, but I will say that it's still in the margin of uncertainty. It's in almost 10 hours of compute. But now, if we switch to the 2 cards being on the same node in the HGX node, so with this NVLink direct GPU to GPU communication, we see that we are saving at least about 2 hours of compute time just by having this faster interconnection. And next, if of course we double the amount of cards, but PCIe, so no fast connection, it's getting faster, but yet not the fastest, because if we have the cards all on the one node with the fast interconnection, it's even faster, and we save again a good 1 hour of training. So again, not in every case it will have an impact, but if you have a lot of transfer, that was typically the kind of task here we're benchmarking, it did have a significant impact on the training time. Okay, so with this presentation of our GPUs, maybe the next question is what to use and when to use it. So there are a couple of things to keep in mind. The first one is if you're tracking your compute units, the cost, with air quotes around cost, is a bit different between the different GPUs. So the cheapest one are the smallest one that we dedicate for development and debugging, this A100 1G.5 GB. And then comes the P100, which are a bit more expensive, and then the A100s. I already say that the smallest A100 are really for development and debugging. But then the P100, where do they sit here? They're obviously not the best of the GPUs, but if your code cannot leverage the A100 new performances, maybe you want to stick to the P100s. But my recommendation will be to first start on the A100 and compare a little bit. If you're having something which is faster on the A100, stick to it. But if it's not, that maybe you want to go to the P100, because there's also the case of queuing time. And if the P100 are more available, you want to use them. There's one corner cases which is interesting to be aware of is for the A100, you'll need your application to support CUDA 11 or above. And it happened to us in the past that we wanted, we helped a user to deploy some legacy code which was running on TensorFlow 1, and at that time it was not supporting CUDA 11. So actually we are a bit blocked and needed to use the P100. So that's something to be aware of. Now, between the two types of A100, well, they're both very performant. You may want to use the biggest one if you have the need for this multi-GPU interconnection, or if you have the need for this largest memory. If you don't, my suggestion will be to have, and we'll talk a bit more about this after, to submit jobs that can use either, because then you have access to a larger pool of resources and your queue time will decrease. And on that note, I'll pass it to Chris.
Thanks, Maxime. Okay, so we've heard about the GPUs NeSI has, and if you're not currently using GPUs, one of the questions you might have is how much effort does it take to actually start using GPUs? And the good news is that in some cases it's not always going to take a lot of effort. You know, there are many codes out there that already have good support for GPUs. So if you're happening to use one of those codes, it might just be a case of enabling GPU support within that code that you're using. Or just giving it a GPU and it'll use it. And that's the case for many molecular dynamics codes and deep learning codes and probably others as well. That they already have built-in support for GPUs. So hopefully you can just take advantage of that. If that's not the case, say for example, if you're developing your own code, or you're using a code that someone else wrote and it doesn't have GPU support, there are a few other options, and not all of them require lots of effort. So, for example, if your code is calling libraries, like doing lots of LAPACK or linear algebra, FFT calls, using libraries like CPU-based libraries, you could just be able to replace those libraries with CUDA, like GPU versions of those libraries, like cuBLAS or cuFFT. And this often involves a minimal amount of coding, so it can be an easy way to get GPUs to be able to use GPUs with your code. Another option is that maybe you can use a high-level framework like OpenACC or JAX or Number. These high-level frameworks they don't require huge amounts of coding. So, for example, OpenACC is a way of telling the compiler that you want certain loops to be running on the GPUs. So you just have to go through your code and identify those loops, and usually it's not too involved. And similar with like Number, for example, you can say I want this function to be running on the GPU, and hopefully it doesn't take too much effort. And the thing that usually takes the most effort to get the code to run on GPUs is if actually you want to code directly in CUDA. So you're writing CUDA kernels yourself, and that can take more time, but it also gives you a lot more flexibility and control. Next slide, please, Maxime. Okay, so getting started with GPUs on NeSI, I mean, the first thing you're going to need is a NeSI account through my.nesi.org.nz. And you can also request a compute allocation there. So you could request a small allocation for testing if you just want to try out using the GPUs on NeSI. Once you have access, there are really two ways that you can use the GPUs. So you've got so-called batch jobs, or you can also have interactive work with GPUs. So on NeSI, we use a scheduler called Slurm. And what this is, you define a job that you want to run, which could be just executing some script that you've got, and you submit that job to Slurm, and then Slurm will then schedule that, and it's got a queuing system, and it'll run that job in the background, and then when it's finished, you can get the results. An example here is a script that defines a Slurm job. So we've got a header section which has got some directives that Slurm understands, which is where you're telling Slurm how much time you're going to need for your job, how much memory you're going to need, and whether you want GPUs or not, and how many GPUs you want. So that's the top section in the example script we can see there. The second section is where you're requesting some software to be available for your job to run. And we'll talk a bit more about that in a couple of slides, but we use a tool called environment modules. And then finally, you actually have the code that you want to run. So in this example, we're just executing a Python script. Next slide, please, Maxime. So the other way to use GPUs on NeSI is interactively through jupyter.nesi.org.nz. So this gives you access to JupyterLab. And you can see in the screen on the right, when you're setting up your connection to JupyterLab, you can request a GPU. So there's a select GPU option. You can request either one of the P100s or one of the smaller A100s. And we highly recommend choosing one of the smaller A100s. If you do choose the P100, you'll be competing with people that are doing batch jobs as well, and you might have to wait quite a long time to get one. So it's much better to choose an A100. And GPU sessions, Jupyter sessions, you can have up to 8 hours for interactive use. A key point here is you need to use a CUDA-enabled Jupyter kernel. So you could use one of the NeSI provided Python kernels, or you could also create your own kernel using a tool called NeSI kernel. And this NeSI kernel tool is actually described in the webinar that's linked at the bottom of the slide. So you can look there for more information. And the other point to make is if you like using notebooks for some reason, notebooks are good, but you don't have, using a notebook doesn't mean you have to do interactive work. There's actually a tool described in that webinar called Papermill that can take a notebook and make it run in a batch job. So that might be well worth having a look as well, if you like using notebooks. Okay, next slide, please, Maxime. Okay, so just a quick note about environment modules. So when you connect to NeSI, you have quite a bare environment, so there's not much software installed there. That's just because we can't install all the different software and versions of the same software that people want to have access to on NeSI at the same time. So we use this tool called environment modules, which gives you this module command, and then you can then pick and choose which software you want to have loaded into your environment at any given time. And you can do that using the module load command. Like, for example, you could use module load miniconda to have miniconda available, or you could do module load Python with a specific version number to make sure you've got that specific version of Python available in your environment. And all these tools, all these modules that we have installed at NeSI, they're compiled and optimized for our platforms. And if you're looking for software and you can't find it, please just let us know at support@nesi.org.nz and we can try and install that for you. Next slide, please, Maxime. And a GPU-specific software. So this is just a taster of some of the software we have that supports GPUs, not listing everything. But we have compilers and libraries. So these are the building blocks for using GPUs like CUDA and cuDNN, and also the NVIDIA HPC compilers, which have good GPU support. On top of that, we have tools like Nsight Systems and ARMForge. These are profiling tools that you can use to try and understand the behavior of your application and improve performance if necessary. We also have Python, and with Python, we've got modules like TensorFlow and PyTorch and so on. We have other software that's built-in with built-in GPU support already, such as NAMD, GROMACS, BASP, Dorado, and AlphaFold, and there'll be many other ones as well, but these are just some examples of codes we've worked with recently that have good GPU support already. And the final point is that we support Aptainer and Singularity containers on NeSI. So, for example, you could go to the NVIDIA NGC catalog, which is a whole host of HPC applications with GPU support in container form, and you can just pull a container from that catalog, and then you'll be able to run it on NeSI. And we have documentation on our support site about how to do that. And it's a really easy way to get started with GPUs if they have a container with your application. Okay, so I think on the next few slides, maybe we have some case studies now, just some examples of work we've done with researchers recently or in the last few years where they've started to use GPUs, just to give an idea of how much effort it took and what sort of benefits they got from using GPUs. So in this first example, we had a project with Wanting Zhao from Victoria University. She's doing protein modeling work using a software called NAMD, and this type of work is very computationally expensive. But we knew that NAMD comes with good GPU support built into it. So we thought it would be a good candidate for trying to move on to GPUs instead of using CPUs. In this case, we didn't actually use the container. So we took a container from the NVIDIA catalog that I mentioned earlier. And following that support documentation, it was quite simple. It's just some slight modifications to the Slurm script to be able to use the GPUs. Because NAMD already had the support, we just had to give it a GPU and it was able to use it. So it was very little effort. And the outcome was we got really good performance. This is on a P100 because it was a couple of years ago before we had the A100. So we haven't updated it for A100s. But one P100 GPU is roughly the same as 3 full MAUI nodes, and that's about 120 CPU cores. So it was really good performance, and we would expect that to be better on the new A100s. So very good performance for little effort in this case. Okay, so next slide, please, Maxime. This was a slightly different case. So in this case, we actually had to do some programming work. We didn't have a software that had built-in GPU support. So in this case, we were working with Damien Mather from the University of Otago. And he's working in the area of high-performance marketing insights. And the bottleneck in the work he's doing is in the log determinant calculation. And this is a very expensive calculation. It has complexity n cubed. So when the data gets big, it becomes a very big calculation. It gets very slow. And the approach he's using is called condensation method. And in this case, we added MPI, which is about parallelization over CPU cores and different nodes on the cluster. And on top of that, we had a hybrid OpenACC to get GPU support on top of the CPU parallelism. And this gave us a 13 times speed up over the serial CPU version. And this was just a simple implementation. So even though we had to do some programming, it wasn't a lot of work because we just said, we want to offload these loops to the GPU, and then the compiler did the rest and all the work of copying memory around between host and GPU. And that gave us a 13 times speed up. Did a bit of extra work to optimize data locality, which meant we explicitly telling the compiler when to copy data on and off, and that gave us an extra 2 times on top of the 13 times speed that we already have, with a downside of a bit increased code complexity because we have to do a bit more work there. But again, we found that the P100s were performing similarly to full Maui nodes. So I think maybe one P100 was running about the same speed as 2 Maui nodes in this case. So again, really good speed up for this researcher. Yeah, next slide. I think I hand back to you now, Maxine.
Yes. So for this next case study, so during this consultancy with MD Saiful Khan from University of Otago, we helped him to port some code on the NeSI hardware. And so first I should describe the task actually. So he wanted to detect some, well, to detect not some birds, but many black-billed gull from an aerial images of braided rivers. And you can have an example. Well, there is an example on the right. So his code was originally developed on a Google Colab notebook, and we helped him to transition to a batch non-interactive version that could run on the NeSI GPUs. And we also offered during the consultancy to test alternative toolboxes, and in particular the Detectron 2 toolbox I mentioned earlier. And for all the good reasons, which are a lot of models, a lot of things you can tune, and really bleeding edge performances. And it turned out that we got a very good results using the faster RCNN model using a ResNext 101 backbone. And so on top of doing this development and tuning for him, we also adapted the code so that it can run the inference on the full image. So here on the right, you only have a cropped version of the full colony image, which actually is roughly 10,000 pixels by 10,000 pixels. But then if you code detection, well, inference as a kind of a sliding window, there are tools to do that. Pretty cool. We can count the birds on the whole image and without using too much of the GPU memory. And I believe that's the last case study we want to present to you today. So that one was another consultancy we did with Kieran King from GNS, and it's about accelerating tsunami simulation on GPUs. So Kieran, so at GNS they have a tsunami simulation code wrote in Fortran, and Kieran rewrote it in Python, but using the JAX toolbox to make it run on the GPU. And if you're not aware of JAX, it's a nice Python package that looks almost like NumPy, but under the hood it has a just-in-time compiler that's doing some fairly good optimization, and it can run your code on CPU and GPUs. And so as part of this consultancy, we helped him to integrate some Fortran code in a Python test suite, so he could compare the results from the 2 pieces of code. And we also did some deep dive into the performance of the JAX code to understand if it was using the GPUs at their best. For example, trying to see, okay, is it running on the tensor cores or the regular cores for the double precision code and these sort of things. Long story short, JAX is really doing a good job at doing optimization. We did all sort of scenarios of benchmarking scenarios to, again, compare many different situations and see if there are ways to improve the code. And in the end, one thing which was critical to get the best performances is in JAX, although I just say that it looks like NumPy, you have specific constructs. And it's in particular, you don't want to loop by hand or use for loops, but you want to use these specific operations, and that will save you a lot of time when JAX does the optimization, the JIT tracing and optimization. And on a large scale scenario, we managed to get a time speed up by leveraging this. And on this note, I think that we reached the end of the main part of the first part of the webinar. And I'd like to thank you all for your attention with this beautiful Royal Albatross chick from Dunedin. And we'll switch to the next part of the webinar, which consists of hearing back from you. So I'll just go out of these slides and switch to the QA documents just to see if there is any audience question. Ooh, no. Okay. Well, if you have any that comes to your mind now, it's a good time. Don't hesitate to put them here, and we'll get back to you in an instant, in a moment. But apart from this, first I'll hydrate myself a little bit. Just have a look at the feedback and increase the font size also. So as I mentioned earlier, this is the part which is a bit more freeform and where you're welcome to comment or unmute or raise your hand if you want to say a word on these topics. So the first thing was, have you used a GPU on NeSI before, and how did it go? So I can see three yeses. Okay, so that's very nice. That's good to know. Thank you. And there was one comment which was, most of the time it works well and right out of the box with a Slurm. Legacy code or code in environment using containers that are prepared by other developers. Oops. I had to rebuild a container as the CUDA version installed and the container was not managed. So unless you mind unmuting yourself, would the person who wrote this comment want to discuss a bit about it, or to explain what was the shortcomings with the versions? That will be very, very kind. Nope.
Hi, Maxim. It's me.
Yeah. Okay.
Yeah, anyway, yeah. So the issue was that I was trying to run a framework about in particular REST Vision, and they basically come in two forms. One is that the developers have packaged the code together with the environments that they have tested in a container. And the other option is that you basically install everything onto the HPC environment. So, but both way works, and I've tried both ways. And in this particular, in the feedback, I was referring to when I was trying to work with the container that the developers have released. And in that sense, at the point, what I remember was that so it didn't work directly because like the CUDA version that they had installed and tested against was quite different from what we have on the HPC. I think in particular was that they had a much older version, and I was trying to run on the A100s. And yeah, at the time I was quite keen to try run on the A100s, mainly because of the memory, and I was processing quite large images, so that's why, and the queuing time on the P100 was very long. So that was the main motivation why I was trying to run on the A100s instead of the P100s.
Okay, so Alan, just a second. So if I understood correctly here, part of the issue was the thing we mentioned earlier, that the container was pre-shipped with an older version of CUDA not supported by A100.
Yeah.
Okay, I see.
So the and they were in Dockers. So I had to rebuild the Docker container. Basically swapping out the older versions of the CUDA with the newer versions, and then convert it to Singularity. So that was, well, I was stuck a little bit there, mainly because I was trying to figure out like where the problem was and everything. But yeah, that was mainly what happened there. Yeah.
Okay. Well, first, thank you very much for your feedback. I'll just use this opportunity to mention a feature that I believe you did not have access at that time. So for people who may not be familiar with how to use containers on NeSI, we don't provide Docker because that will mean that we need to give you root access to the HPC, which we don't do. But the alternative technology are Singularity and Apptainer. You can pull a Docker container in Apptainer. It almost works all the time, and something which I believe maybe Alan you encounter was if you need Docker Compose, maybe that's a bit of a different story. But for simple, let's say containers, it should work. And the downsides, if you have application like deep learning, is the containers can be heavy. That's the least to say. Think about 10 gigabyte containers. And now we have some way to build containers on NeSI. It's not bulletproof, but if it can save you time in terms of not having to build the container on your end and then ship it to NeSI, that you can have a try at it. We have a documentation. We'll probably send the link in the email after the webinar. Okay, I think I've seen some questions popping up while we were talking, so I'll just go back to the questions. So first question, why does code need to be rewritten to run on the GPU? Do you want to comment on that one, Chris? I don't know if you're the one who answered that one.
Oh, I was just answering another question, but I didn't answer that. But basically, the GPUs are different hardware, so I think they don't understand the instructions that they don't understand CPU-based instructions. So you need to there's just a different model for programming for them, I guess. So that's why code needs to be rewritten for them so that it could then be offloaded to the GPU and run there. I guess you don't need to. It's not always true that it's possible. Some of the programming APIs, like for example, I mentioned OpenACC in the talk. I mean, in that case, you don't actually need to rewrite code necessarily. With OpenACC, it's similar to OpenMP if you used that before, where you just place pragma statements around loops to tell the compiler to offload those loops onto the GPU. So yeah, and if you can compile the same code without GPU support, the same code in principle would run on the CPU. So you don't actually need to rewrite code in that case. It's more like just adding information to let the compiler know what to do with the code you've already got. But yeah, if you want to go the CUDA route and write, you do need to write your own CUDA kernels, which then are understood by the GPU, the compiler, to run on the GPU.
Thank you, Chris.
Something, yeah.
I hope that answered the question. Also, there was already an answer here. Okay, next one was, I'm about to do a postdoc overseas where the group has their own server. We are thinking purchasing GPUs for doing machine learning on. How did the A100 and P100 cost? And do you need to purchase specific machines for those GPUs? I don't think we can discuss the cost in a publicly recorded webinar. I'm sorry, but probably you can get in touch with us and we'll see if this is an information that we can discuss. I can't promise that we have the right to discuss this sort of topics. Sorry. I know that just the A100 you need, you will need some specific hardware to have the proper cooling and things like that, and also a good power supply. The next one is, can you share the Slurm option to use a full GPU, whatever, which one on Mavica? Yes, so that's something, yeah, that will be sent also in the webinar, sorry, in the post-webinar link, and you can find as it has been linked here. And actually, there's a nice thing, the person who answered that one, probably Chris, oops. You have here what I highlighted is this multi-partition submission. So for people who are curious about how do I request any A100, that's how you do. You specify HGX or GPU partitions, and that's where Slurm will decide whatever is available. The downside of this is you need to make sure that you won't need more than 40 gigabyte of GPU memory, because if you need the 81 and you end up having a 40 gigabyte memory GPUs, well, your code won't run. Okay, so time flies. So I'll just go back to the audience feedback questions and go through them. But again, if you feel that there is something you want to share, again, you don't hesitate to raise your hand or unmute yourself. Okay, so the thing I think we were asking you to think about, and if you have any comment right now, don't hesitate to type it in, is there anything that's stopping you from using the GPUs? So bottleneck for obtaining access sometimes it requires extra debugging because there are aspects that don't initially work on GPU that need sorting out and difficulties to debug and optimize the code. I don't know. Would you mind, Gemma, commenting on the difficulties to debug, or is there something you'd like to comment a bit more about?
So I hope I'm audible. It looks
Yes.
like I am. So let me think. Often it's really frustrating things like I'll be using machine learning codes, so TensorFlow or PyTorch or that sort of thing, where in theory it should just work exactly the same in terms of the code you're writing, and then the back end handles it for you. And you'll be expecting it to go fine, and then it'll throw out some error message that you can't comprehend. And I've used the NeSI office hours actually a couple times sorting this out because I get weird error messages. Often so memory issues are quite common because I'm often using the P100s, which don't have much memory. And when you do get errors that are GPU related, often they're not very informative in terms of what they tell you, and trying to figure out what on earth is going on can be a lot of back and forth Googling error messages and discovering that whenever they showed up for other people, something completely different was happening because it's just not good error messaging in general with a lot of these things. And it's harder to figure out what's gone wrong.
And just as an additional question, so were you doing this sort of development debugging using batch jobs, or were you using interactive notebooks, or?
So I've actually had issues sometimes where something will work on interactive and then I try to run it as a batch job and it won't. That was a fun one. I think it's partly because the modules don't work in precisely the same way on interactive and batch. So things like if you purge modules on interactive, it will keep some things, but if you purge them on a batch job, it will actually get rid of, or maybe it's the other way around. It's one or the other. It's something like this, like the same command in an interactive job and a batch job will not necessarily do precisely the same thing. So yeah, I have had issues where it was working interactive just fine, and then as soon as I go to a batch job, it's dead.
Okay, well, thank you for this feedback, Gemma, and yeah, definitely something we need to sort out. And also thank you for mentioning the office hours, because actually that's something we have in place and we don't talk enough about probably. So remind me if I'm right, Nisha, it's every Wednesday, right?
Yeah, every Wednesday.
So every Wednesday we have an office hour of 1 hour, which is come. And if you have any problem or things you want to discuss with us, we're available. And yeah, it's really a walking, well, virtual. It's on Zoom. But yes, when we can try to help you debug the code or difficulties. So yeah, don't hesitate. Usually the people feel a bit lonely during their office hour waiting for people. So really, you should not hesitate, as Gemma mentioned. Thank you again, Gemma, for this. Okay, we're almost at the end, so I'll go through the last bits. So what do you use to run your code on GPUs? Singularity, Conda, Python, Jupyter Notebook. Thank you, Gemma. Slurm and Silk. Oh, wow, someone is using Silk also. That's quite cool. So Silk is a workflow management system and based on CUDA and C++. Okay, I'll be curious to know if anyone has experimented with some MLOps type of code. That's my personal interest here speaking, to sequence experiments and run code. And just letting people think a bit about this, is there anything, any burning need or something you'd like to see next on the NeSI GPUs? So would like more GPUs, more software, or specific training in some topics that you have not seen addressed and you'd like to be upskilled in that space? That's your moment. If you want to let us know, because that's the purpose here, is to get from you some feedback about where we can develop material and help you best. So again, this document will stay available. So if you want to add the information later, you're more than welcome.
I guess I have, this is Alex, but I've used GPUs in the past and so forth. But maybe one thing that I noticed, and I believe it's still true, but needs a little bit confirmation, is that the GPUs seem to be evolving faster than the CPUs. So, one thing that we tend to see is that CPUs are just not getting much faster over the years. We get more of them because we get more cores, but the CPU per se is not getting much faster. And whereas the GPU, I think between the P100 and the A100, I think you gave an estimate of a factor like up to 5 or something, I think, and we've seen pretty amazing speed ups. So also in terms of the increase of memory. So I was wondering if either one of you would comment on the sort of future trends. If a researcher is sort of sitting a little bit on the fence and should I jump into the GPU pool or will this be a technology that is likely to disappear in the next few years and the CPUs might catch up? What's your opinion on that?
I'll give mine, and Chris, just prepare yourself because I'll ask you yours. I'll just say that let's see. When I was a master's student, which is not yesterday anymore, I was already doing a bit of CUDA coding at that time, and so I think we can say that it has been around for quite some time. So, and hoping that we can predict from the past, probably it will stay around for quite some time. And if we compare to other technologies, so there's usually a lot of announcements about other type of accelerators, because here we focused on GPUs, but people could say like, I want FPGAs, for example. And that's only my personal opinion, I'm way more confident into GPUs stay around than other specialized hardware, which come and go and have their specific toolkits. And here also NVIDIA did they really managed to get everyone around CUDA for the better or the worse. But it means that, yeah, at the moment, for a couple of years, you can probably invest in this and be confident that it will stay around. What's your opinion on this one, Chris?
Yeah, not much to add, but yeah, I think more community codes, like big community codes, seem to be adding GPU support. So the trend seems to be to adding support for GPUs rather than taking it away. And lots of the bigger HPC centers now seem to be having large numbers of GPUs attached to them to be able to get really good performance. So I think they're probably here to stay for a while, I think.
Also, there was something which I mostly work in sort of higher level languages and probably mostly Python. And the packaging story also have involved a lot. And it's not yet fantastic, but it's getting way better than it used to be in terms of having something which can run on CPU and GPUs. If you look at the latest version of TensorFlow, now you only install one version. You used to have to pick between, do I want the CPU flavor or the GPU flavor? So also in terms of shipping an application, I feel it's becoming easier. Don't say easy, easier. I think we're almost at time. So, and thank you for everyone who added training ideas. We'll take them and think about it. But because we have 5 minutes left, I'll stop sharing and I'll leave the mic to Nisha.
Thank you, Maxime. Thank you, Chris. I am now going to try my best and find the right slides. Here we go. So thanks again for attending this webinar and for asking questions, starting discussions. This was great. And the other thing we wanted to leave you with was a quick look at some of the events that are coming up that NeSI is helping or facilitate or be part of. So there's the New Zealand Research Software Engineering Conference that's coming up. It will be online from the 18th and 19th of September. Registrations and submissions are now open. So please do go check them out. And we have the eResearch New Zealand conference. The dates have been announced, so this is just to save the date for that. It's going to be in Wellington, so from the 7th to the 9th of February next year. We don't have the website or other links yet, so watch this space, and it'll definitely be available on the NeSI website and newsletters. So keep an eye out for that. So just a few words before we wrap up the session. Do join our mailing list for training alerts, newsletters, event announcements. And if you've got any questions or feedback, please keep an eye out for a post-event email that will be sent soon. So like Maxime mentioned, we are going to make sure that we'll include all the links and resources that were discussed as part of this webinar to be included in that post-event mail out. And another shout out to the weekly online office hours that we run. It's usually every Wednesday, and we alternate between mornings and afternoons. So we'll also link a page for that. Thank you for your attention, and hope you have a good rest of your day. Thank you.